Okay, let's use Black-Scholes equation to derive Black-Scholes formula describing put and call, or a general way to solve a Black-Scholes differential equation. So assume V is a derivative of a stock given an R return mu sigma, where S is the stock price, time terminal pricing. Anyway, so this is a Black-Scholes differential equation we derived from the previous video, and this looks relatively complicated. We can simplify it and transform it through a few transformation. Define tau. Note that the tau is not just t minus a big T minus small t, where big T is the terminal time. It's come handy in the future. This is one way to make it unitless, so that tau is a unitless number that will come in handy in the future. And x is ln S over k, where k is the strike price. So we could plug that in to translate the dt and dt grad and the Laplacian to in the coordinate of tau and x. D tau can be expressed as 1 over d tau multiplied by dt on both sides, and t, based on this formula, t can be expressed in this way: big T minus 2 tau over sigma squared. And then the simple derivative, this is 0, and then we have negative 2 sigma dt. For ds, similar thing. dx both sides, and then x is ds dk ln s over k, and do the chain rule, the ln s over k over ds over k, s over k ds. This become 1 over this become 1 over k, because this goes to 1, and this is 1 over 1 over s over k, so it's k over s. K cancels out. We have 1 over s dx, and ds. We have this coming from what we already derived here. Ds, you can consider as a 2 separate variable, dx. Then we have this act upon 1 over s, which is this simple, and then just 1 over s and ds and dx. And now we know ds is this. Just plug it right in and get this. That's the final answer for the ds, which is Laplacian, can be translated from s to x. So plug everything in, the d tau dt, and gradient Laplacian. We got this. So this is the dt here, and gradient, and here is a gradient. Here's Laplacian. Here's the Laplace. Here is the Laplacian. Plug everything in, cleaning it up by merge dx here, and then multiply 2 over sigma square, so that to get this out of the way, to make it look a little bit more pretty, you have this. So you put tau on the other side, and then just flip tau on the other side, so become positive, and then the rest is here after multiplying 2 over sigma square. To further simplify it, we define kappa mu as 2 mu over sigma square. If you find it confusing why I keep mu, it's just for my own benefit to see like where this mu goes and where this r goes. We know that Black-Scholes equation, the mu equals r for the hedge portfolio or risk-free return. The risk neutral return. Anyway, it's just easier to see where it's coming from, where it goes. So we got this. We kappa r 2r over sigma square 2 over sigma square. Just plug this in and plug this in to make it look pretty. We got this. We got this expression, and we ultimately want this, right? We want a nice and clean diffusion equation. But we left with this. We can do a further transformation because it looks awfully familiar with our our experience with a lot of exponential. We do this transformation and see if we can plug those out of this. Let's assume v equals exponential alpha x plus beta tau u. Plug it in. We know that d tau v is this, so acting upon this and acting upon the u. Dx, same thing, acting upon this and then acting upon u. Dx square, same thing twice, so it looks almost like a quadratic, similar to quadratic. And then we multiply, because the exponential always exists, no matter what you do to it, or just multiply the inverse of that to get rid of that term. So life with this have beta dt and the whole quadratic term, and this is 1 dx. It's this from here. This thing that doesn't change, but change to u, but there's an exponential. Anyway, cleaning it up, grouping everything by u, dt du, that's what you want. That's what you want. That's what you want. Let all go to the left-hand side. That's what we have. And group everything by u, dxu. U, we have beta alpha square alpha kappa mu kappa r. We have this. And then group everything by dx du, this and this. In order to let this be gone for any u, then we just need to make sure these are always 0. So we're left with those two equations. Well, two unknowns, two equations, and it's just a matter of solving alpha and beta. This is trivial to solve. It's 1 over half kappa mu 1 minus 1, and plug it back into this equation. We will, well, because this is negative 2 alpha, we have it here. Just put the beta on the other side. So it's alpha minus 2 alpha minus kappa r. So it ended up become beta equals negative alpha squared minus kappa r. So we now we have v equals exponential alpha x plus beta tau u, where alpha and beta is such. In the case of mu, kappa mu equals kappa r, we have this for beta. Just for note checking, because there's a link of a undergrad had a thesis. There's a few typos he or she made. Anyway, so with this transformation, we have d tau u Laplacian u. Laplacian is a two-order derivative with u equals this. So that's the transformation we have to give us from a Black-Scholes formula, Black-Scholes equation, partial differential equation, to a diffusion equation with to review this transformation and this transformation. So those two transformations will give us a diffusion equation. So next, we'll make a guess, as any good physicist would do. On solving a differential equation, make a guess. Is a Gaussian somewhat a convolution with a Gaussian. This is a Gaussian, and this is the initial condition. At least for me, intuitively thinking, it sounds awfully familiar with some type of, actually with any differential equation, but for me, it's intuitive to think at in quantum mechanics, we have eigenfunctions, and then we have an initial state, and we have two brackets, and sum all the coefficient, and then this is almost exactly what we are doing. We found an eigenfunction which is a Gaussian for diffusion equation. For general solution, just to for our benefit and future usage, not just for finance, we add a gamma squared there, where for our case gamma equals 1. So we guess this is a solution. Let's check if it's correct. So we plug it in as a diffusion. First, look at the left-hand side. We put everything in, acting upon here and here. So this is trivial, just 1 over square root tau. And using Leibniz, I don't know, something's rule, and you can, because it is integrating through y, is independent of x, you can actually put the derivative inside. So we can just put the tau inside, d tau inside of here, and then directly acting upon the exponential, which is trivial. It just using chain rule, exponential doesn't change, and then tau 1 over tau become negative 1 over tau square, and then negative sign cancels out. So we have this. So we add up this term and this term because it's acting upon this and this. So we have this to here, this to here. You can slow down and double check everything, of course, it's a video. Laplacian of u, right hand side here, we will have similar things applies using this rule. We apply it Actually, nothing here, only on the exponential. Just do the exponential twice. You do a derivative once here. So this only thing is here is y. Doing it so doing it on x. Yes, doing it on x, you will have 2x minus y, and the exponential doesn't change. And do another derivative. Is one acting on this, another acting on this. So this squared is acting upon this, and then this will be acting upon this thing will be 1. Since this is 2, this is 2, this is 4, 102. Right. So we have this term to here, this term to here. And then we plug everything in, left hand side, right hand side. And this is this, this is this is this, multiplied by gamma square. Apologies. Gamma square. And this is here. So now we proved this indeed is a solution to a diffusion equation in this form. And we can use this, just need to plug into whatever derivative, to my understanding, whatever derivative you want with assumption of Black-Scholes equation. And we will do that. Since for our case gamma equals 1, we just plug it in, make it to 0, make it to 1, make it to 1, then we're left with this expression. So to make it even more pretty, we transform y minus x square root tau to z, and then thus dy equals, we plug this back in here, becomes square root 2 tau dz. That's pretty trivial. You can just do the derivative on both sides and you'll see what happens. Then we're left with there's a 2 multiplied by 2, and this becomes z squared. So we're left with negative z squared over 2, and this is dy. It's quite pretty. And then you multiply. Here there's a 2, there's a tau. It cancels out, and this looks very pretty because it is a Gaussian. This is a Gaussian. This is the error function, and then this is the initial condition. So let's look at the call option first. Call option is I don't know if I can recite the definition, but at the terminal time, the payout is S minus K plus. So when it's greater than K, which is strike price, stock price greater than strike price, then it just whatever left of it, and then below that is 0. So this can be expressed as K maximum y minus 1, where is ln S over K. Then this become S, this become K. So just follow me here. So recall y equals s over k. We'll put it here for the case ln s k over greater than 0, which is s greater than k. This is a little bit backward, isn't it? I'm sorry about that. And exponential 0 equal to 0 because of the maximal. This is the condition. And then this become s over k. This become 1 minus 1 is 0, and s over k. So this is the payout at tau equal to 0, or t equals to tau. T equals to big T termination. The expiration time. So we can just use this as a boundary condition. And we will recall u equals v exponential alpha negative alpha x minus beta tau. Then the boundary condition for u based on this v, which is the actual derivative boundary condition, we remember the transformation we had, will be this: adding exponential alpha y minus beta tau at tau equal to 0, and this will go to 0. And this goes to 0. We have k exponential. Plug it in. Plug this in. Exponential y k and exponential max y 0. Then we know when y less than 0, this is 0. It's nothing. And this can be translated into z less or equal to negative x square root 2 tau right here, because of the transformation we had here. This is annoying. Okay. All right. So so this maximum condition goes away by adding the boundary. Instead of negative infinity, become negative x over 2 square root 2 tau. And then we add the y, add the other transformation back. Y equals x plus square root 2 tau z minus 1, and the alpha y, negative alpha y is the same thing here. And then, of course, don't forget exponential Gaussian, negative z squared over 2. And we can multiply this into two terms. One has this, another have this. So let's do this first. So this become alpha x, alpha 2 tau, and negative z squared. And then multiply, and another one is this whole thing, because it's 1, multiply by this. And then essentially you just add another term here, with the rest detached, intact. because it just add additional multiplication because it's in the exponential. All right, and then we group them together to exponential. This is this, and this is this, so that we can look at it in one page. There we go, beautiful. And -2 z squared. It's just simple algebra. I will just run it through quickly. 2 alpha, because there's a half, then you add 2 here, and then you have alpha, and then do a square. You're left with this minus x, alpha x. Two, and then cancels 2, then you have this. Same thing here, except for the one that associated with z, we have 2 terms here, become negative, so this become positive 2, like alpha minus 1, because this is negative, this is positive, and then alpha minus x, alpha minus 1x, and then you take the square, then you have a square of this term, so you have to make it, you have a additional minus this, half minus this, so you have to make it equals, then you have a plus half alpha minus 1 squared 2 tau. There's no z here. And minus this, just to clear things up, we have the square 1 over 2 and 2. Then we're left with this expression. So plug everything back in to make this transformation dt, there, and there, become this. And this is the first term, the second term, just plug everything back in, that's it. And C1, C2 transform to here and here. To make it look even more pretty, plus alpha square root 2 tau, alpha minus 1 2 tau, and then you have a beautiful error function, and then left with just a number, because it had nothing to do with c, or another word z for this case. We define n alpha as 1 over square root 2 of these, so pretty much integrated as the error function. And since it's due to symmetry, you integrate it from a negative infinity to alpha equals to from negative alpha to positive infinity. That's just symmetry. So it also equals to this. And observation here, this is the same, in the same format, plus a square root 2 here. And we have negative k n x, so this negative of this x square root 2 tau minus alpha square root 2t, and then multiply this constant right here. Similar thing, I'll be quick, this one here and here. Then that's pretty much it. And then we need to put everything back by transforming it back to what we are having. This is a solution to U since V equal to this with alpha x beta tau. Put it back in. We call this exponential. Just trust me, I got everything correct. Or you can just double check alpha square tau minus x, and then x minus 2 tau x squared 2t, and then alpha minus 1 squared tau alpha minus 1 x, and then plug everything back in to V. Since the beta is this, beta tau is this, so plug it in. You see a lot of cancellation. Left is kappa r. Same thing for the later ones. For the next one, you have alpha square minus 2 alpha plus 1 tau. So this goes, and this, no, this does not go. So you have this, and this goes. You have an x minus minus, and you have this. So this is one more. Now the transformation to V is complete, and we need to transfer everything back to alpha with alpha minus 1 x, and kappa, definition of kappa, and definition of tau. All of algebra we need to do, just put the x in, x here, and then tau, put the tau in, and then put a kappa in, because alpha is a function of kappa mu. Put the kappa in, mu, kappa mu. And since exponential of x is s over k right here, we can make this s over k multiplied by k equals to s right here. And then plug in the definition of kappa. Put kappa in. Kappa in here, kappa here, kappa here, kappa here, here and here. And then this is k, s over k. Then O cancels out. You have mu over r, exponential of r. I just noted it is change the order of this, but it's the same thing. Positive, this become s because k cancels out. You have this, and you have this. So this is a call option equal to this long expression, but we formulate d plus minus. So square ln s over k mu t minus big T plus or minus sigma t over t minus t over 2. Sometime d1 equals d minus, d2 equals d plus, and it's just another naming convention. And so a risk neutral market, mu equals to r, and then this goes to 1. Oh boy, and we are almost done. This is call option, and then similarly we can calculate the put option, which is which is like this. It doesn't go over zero, because stock never goes negative. But I'm too lazy to erase it. Okay, so the payoff of put equals K minus S plus. So if go below the strike price, you get the payoff of the difference. And before that, you get 0. Betting against the stock. And then similar line of thoughts, it just become a minimum of a ln s over k over 0. That's I guess I hate to say that coming from a student. This is left to the readers to exercise because it's just almost exactly like what we did, and it's a mirror to what we did. It's like a highly symmetrical. So as the audience of physicists, I think you can do it. I mean, other people you can do it as well, but anyway, it is more intuitive maybe to physicists. Ln s over k. Put it back in, you got the same thing like what we did. Remember kappa of k, and then there we go this. And put it into boundary condition. This is u naught. Put in the boundary condition, we'll have this. So it become, instead of previously was 0 to infinity, now infinity now was negative infinity to infinity because of the reverse. It becomes symmetrical about the point of k over s. Or s over k. Anyway, compared to the call option, we have this. Just and we go from the positive to negative. We have this, and then this is just almost exactly the opposite. You have s over k, and the positive sign become negative sign of the where it integrates. But the exponential doesn't change location because of the exponent doesn't change exponent doesn't change location. Thus, the put option pricing using Black-Scholes differential PDE. We have for the risk neutral market. We have this formula for put and call options with d plus minus equals to that. And there we go. Just a overview of everything. We go from equation go through this transformation. This transformation giving us a diffusion equation, and then we'll make a lucky guess, but it's correct. It's a Gaussian. Diffusion equation is a Gaussian and then you can add this boundary condition, and then we apply the boundary condition we are having, which is this. It's a call option, and plug everything in, solve to get expression of u, and then we transform everything back to v, and solve this everything, and then this is solve solution to u, and then we transform back to v, left with this. We got this, we got the call option, we got nice formula. For risk neutral, this go to 1. For put option, it does almost exactly mirror about S over K equal to 1. Or ln S over K equal to 0 is a mirror. Then solve everything. We got the formula for put and call options.